fix it to any point you want. And so you multiply this by the corresponding, by this box. And you normalize it. And so this thing has, you have to normalize this integral. So you're going to decorate this by this, this two-loop integral. And you're going to normalize it so that it evaluates to the identity at any particular point you want in the xy plane. So even though there don't exist special points where there are residues, who cares? Pick any one you want and normalize this. So this thing is going to have a normalization that depends on x and star and y star. But the good news is that this is not a spurious propagator or anything like that. This is just affecting the normalization of the integral. And any choice results in a dual conformally invariant integral. Everything is fine. And again, it's matching field theory along this codimension 6 residue, on this codimension 6 cut. So you're just matching it as a full function of this. This. And it doesn't have any further cuts, and so this is uniquely fixed. Okay. So we include this, and now we're guaranteed to match that kind of a cut. Okay?
You have to know that there aren't any tensor integrals in that topology, right? Using dual conformal invariants.
That integral is you. Do I need to?
Suppose we weren't in n equals 4 superangles at this one. Very high rank tensors.
The normalization of that integral on whatever point you choose is going to be independent of L. I mean, it's just a function x star. The normalization is just going to be a function of x star, y star, and the external kinematics. There's no tensor numerator or anything else. It has no other physical cuts. This is an ingredient in any field theory.
Okay.
Yeah. Yeah.
Yeah, I have a question. It seems that for this kind of co-division singularity, actually get this kind of curved picture.
Yeah.
But I would think that generically, if you go beyond this n-4 theory, you would eventually get to more than one master integral. For example, in my example, get 5 master integrals. They are really linearly independent. I think, is there a way to fix all of them without using this kind of curve, this kind of integral?
There's no way to get rid of this. There's a single component that is just this elliptic integral and nothing else. So you need to include the elliptic integral. There's no way around that.
No, my question is, so how do you read all this kind of coefficients, not just for the scalar integral, but also for the tensor integral? That's my question.
Again, the story is, what would happen in a general field theory is that this thing is going to depend on more things, and that's going to give you this tensor, the numerators. And n equals, if you evaluate, you can evaluate this on-shell diagram.
Sample it at more than one point to extract those coefficients.
And you fix each one of them, one at a time. So, I mean, this actually is very close in spirit to what is done in maximal cut language, right? Instead of actually cutting, instead of insisting on going to codimension 4L cuts, you just insist on cutting maximum number.
That was done
exactly
with the 2 particle cuts.
Yeah, and that method clearly works, right? There's no question about that. This is a good strategy. I'm ashamed how long it took me to realize that this was the solution here. I wanted to get to cheat somehow, but okay. Anyway, so now we've matched the codimension 6 cuts, and again we've matched everything that involve codimension 6 cuts that involve 7 propagators. But we've not yet matched field theory everywhere because there are a few more leading singularities. There are a few more codimension. Now there are codimension 8 cuts that we can fix, and this is actually going to be really important for us. So the next kind of on-shell diagram that we know the field theory has to be corresponds to, that's linearly independent of everything we've written there. This is important. Is a pentabox that is massive on the left. I need to emphasize that because if there was one massless corner here, then it would be accessible in terms of residue theorems by what's already been written. So we're exclusively writing finite pentaboxes. So pentaboxes with massive size. And of course, it depends on the chiral. This depends on whether you choose one solution or the other. And to this, of course, we decorate the obvious pentabox. Okay. And again, there's a different numerator depending on which solution you do. And this again is just normalized to the unit on that. Now, this is why it's helpful to go in the direction we're going, starting with the most singular things and going to the least singular things. And the reason is because the condition the normalization, if I just told you that this integral is normalized to match this cut, that is not sufficient. It is not sufficient exactly because you can add and subtract to this integral any double box to it, and it will not affect its cut. It's a cut involving these 8 propagators. And so the normalization of this, in order to uniquely specify this normalization, you need to say that it's unit on this cut, and that it vanishes on all of these heptacuts. So this normalization also depends on x star and y star, and all the possible cases, because there's an x star, y star for every possible topology. But the point is that so this is uniquely normalized by the condition that it mapped the cut above it, and that it doesn't screw up anything we've already mapped. Okay, that's good. And then finally, the last kind of leading singularity, the first one you encounter if you start from MHV and go upwards, but anyway, is this kind. It's a kissing box, not very difficult to compute in field theory. So it's an isolated leading singularity, and there are 4 of these. There's an I and a J, depending on whether this is quad cut 1 or quad cut 2 on which side. So there are 4 possible things of this topology. And you decorate it by a double pentagon. Now historically, these double pentagons had wavy line numerators or whatever, but this doesn't depend on momentum. It doesn't depend on how you choose to represent anything. The point is that this double pentagon is uniquely normalized by the following conditions: that it be unit on this cut first, that it vanish on all pentaboxes that are part of it, that are of this topology, and that it vanish on all of its hexacuts. That uniquely fixes what this expression, what these integrals look like, which will depend on x and y. But we're guaranteed to have not screwed up anything we've matched, and we're guaranteed to match the field theory on this. And these 6 terms give us the right answer. So to demonstrate the non-triviality of that, I know I'm going to wrap up soon. So we released a package that computes this in this representation in terms of local integrals. And we also did this by BCFW, which is also prescriptive. For those of you, just in case it's not entirely obvious to everybody already, the reason why BCFW is not good enough is because although it's completely prescriptive and concrete, and it's easy to evaluate in Mathematica, you just spit out the answer. The problem is that term by term, we have no idea how to integrate any of those terms. They're non-local, they have these non-local poles, so we don't know what it is. But but BCFW will spit out a rational function. And at 10-point n cubed MHV, it's a really horribly complicated rational function. But we put it on a computer and checked that BCFW matched this exactly as a rational function, all the way up actually to 14-point n to the 5th MHV amplitude, which is overkill, but it was also kind of just showing off by how powerful these packages are. That you can evaluate that this is totally within reach. You can just represent it this way. It's a very straightforward procedure, and it's because there's no linear algebra involved. We're literally just writing down the integrams. These things are uniquely fixed, and once they're fixed for all field theories. You can match this cut in any field theory for it. So this gives you a nice prescriptive thing. I probably have no more time, but I want to emphasize that this idea of going back and going to a lower cut and fixing that is actually what we should have been doing even at one loop. And at one loop, in n equals 4, it would have been a little silly, because we would have included bubbles. And then we would have included triangles normalized so that they cancel on all the bubbles we already matched. And then we would have included triangles, or that we would have included boxes normalized so that they don't map, that they don't screw up the triangles and the bubbles. And at every single step, we're adding and subtracting the same answer. And so it seems like horrible overkill for planar n equals 4, but it is the correct and general procedure and is guaranteed to match the maximal cut approach that we do in general field theories up to, somebody should ask about this, but up to rational terms, which this is not capturing yet. It's all very 4-dimensional. So, okay, I'm out of time. Thank you very much.
When we are dealing with non-planar multi-loop diagrams, we need to invent a trick, introduce an auxiliary external momentum, and then set it to p equals 0 at the end of the calculation. When we have to deal with 2 consecutive the white bubbles or 2 consecutive black bubbles, we introduce auxiliary BCFW bridge,
Yeah.
and then set it to P equals 0. I wonder is the same as this your trick that double cut your.
Oh, it's not that different. So I mean, I'm not sure if this is exactly what you said, but when I want to write this, for example, the easiest way of doing that is to actually think about this as I can't do it without erasing. This is basically, I think of X and Y as these BCFW bridges. So I start off with something, this kissing boxes, which I know how to compute, and I just BCFW shift it. Is that?
We only have to invoke the trick when we are faced with two consecutive white or two consecutive black bubbles.
Okay. On the inside or the? I mean, on the outside, that vanishes.
No, in the inside, and then we have to, no, they're attached to its external line.
Yeah.
And then we have to introduce an auxiliary external momentum with the opposite color, and then pretend that it's a good diagram, compute it, and then eventually set the one that we introduced, the external momentum we introduced to 0, to recover the original diagram. And it would look conceptually like the trick you were using, cutting the same line twice.
Yeah, I think so. I think so. Yeah. So I have the intuition that this is going to generalize to non-planar, and it's going to look a lot like that. But I don't know exactly. I haven't worked out the details. I don't have much concrete to say. I think what the bottleneck or what needs to be done is to work out exactly which cuts we need to match all of them. So there's a field theory side, which is that if you match all of these planar cuts, you're done. And in non-planar theories, you need to match some minimal set of non-planar cuts. And I don't know if we understand, well, I don't know if that hasn't been worked out yet. Yeah?
What about lower supersymmetry? If you have equals 2 or giving QCD, do you have any ideas how to generate it?
Yeah, I mean, it's going to look like this. I mean, so these pictures don't have anything to do with n equals 4. I mean, this picture is defined and meaningful in any quantum field theory, right? There's just product of trees and stuff. So this story, now the difference between n equals 4 and n equals 2 or 0 is that there are more pictures, right? So there are triangles and things like that contribute.
You're also using dual conformal integrals here, right? That's what you said, right?
In this case, they all happen to be dual conformal, and which is nice. It means that the ratio function is manifestly so. But that's not really the important thing. The important thing was to decorate an individual cut with the integral designed to match that.
But do you know what sort of integrals you should use when you have lower supersymmetry, or
Right.
that's something you're going to look at?
Why aren't you going to need those other master integrals Jan was talking about?
They're going to be generated by this, but it's not going to be generated at the integral. It's not going to be generated by the decoration side. It's what's going to happen in for these other master. I mean, what's going to happen in n equals 2 or so. So the one loop story should look more complicated than the way I've written it in general. It should start with bubbles, go to triangles and boxes, and chiral boxes like this. And you start by matching the bubbles, and the bubbles is just the integral that we're going to decorate it with is just 2 propagators, fully scalar, and we're going to evaluate field theory on this bubble. Now, all of the tensor structure is going to come by what those product of trees are. So those product of trees depend on the extra parameters, x and y, in this case. At one loop, it'll be a bubble is a function of 2 parameters.
The one loop is too simple because all the tensor boxes can be reduced algebraically without using IVP down to triangles.
Oh, well, I mean, okay, the story is the same. So at two loops, we're going to get these tensor contributions to things like this, are that when you evaluate these trees in the field theory of choice, they're going to have all sorts of tensor structure. They're going to depend on x and y in some complicated way, and that's going to appear here. But this is just a scalar integral normalized this way. All the extra numerator stuff, all the extra tensor stuff is coming from the field theory coefficient.
So are you just going to match to one coefficient, or are you going to have more integrals with that topology that you're going to match to?
I'm going to match 1.
You're just going to match one.
Yeah, this thing is going to be a complicated function that's going to basically amount to the whole tensor numerator that should be attached to this denominator. Yeah.
Yeah, question. So how do you deal with the low cut? For example, if you consider like n equals 0 theory, suppose you have some kind of sunset diagram, how do you perform this kind of cut? It must be quite difficult, isn't it? Because the dimension is so low like this.
I wish I had something more concrete to say about it. I don't know. Yeah. I don't have a good answer to that. It's a good question. Yeah.
So there you show a pentabox which has two massless legs.
Yep.
There you show one that has two massive legs in the
Yes.
same place. What about the case where one's massless and one is massive?
Yeah. So
And
that's.
doesn't that have a divergence?
It does.
Divergence?
Great. Yeah.
Yeah.
So
Where's that one sitting?
inside here. So the so the
In some limiting case of the
no, it's attached by a residue theorem here.
Okay.
So this yeah, this leading singularity is related to, there's a residue theorem that involves not cutting this one, and that's going to break it up into a single massless leg and then massive legs over here. So there's a GRT that relates this guy to all of the other ones, and so yeah, so we're guaranteed to match that cut from what we have already. We're not including that integral or that integrand explicitly at all. Yeah. Oh, but I should make it very clear, but I think there's an important point there, which is that this is another big distinction between the OPP, or the integral reduction technique. The integrands I've written down here are not complete, and they're also not all independent. Okay, so these integrands are not a complete basis of integrands, and they're missing things like that, which are linearly independent as integrands from what we have. Right, so that scalar integral with a single massless corner is independent of these ones, and it would be needed in a complete basis of integrands. We are not including it here. This is not an expansion into a complete basis. This is expansion into a good enough basis. So this matches everything, and it will match all those cuts by residue theorems.